Final session of the WebAssembly workshop and our final keynote speaker. Last but certainly not least, we have Chris Woods talking about software engineering economics for runtimes with a code name that I'll let him explain.
It takes a long time for me to get to the point, so in this talk I'm going to start in 1987. 1987 is a big year for computer science. It's the year that Windows 1.0 was released. It's a big year for culture because it was the first time we ever saw Bart Simpson on TV. But most importantly for this talk and this story, it's exactly 10 years since the release of Star Wars. George Lucas, its director, is now quite wealthy and very famous. And at the time, he decided it was the right moment to enter the computer game industry. So creatively, he came up with a game studio called Lucasfilm Games, and we now know it as LucasArts, and it's part of Disney today. He said, look, we're going to create a game, and I'm going to challenge the LucasArts games team to create a movie-like experience with a home computer in 1987. I'm not too sure if this computer game thing's going to work, so you can't use any of my IP, which means you can't use Star Wars. So create your own story. And you have to make money. Now, to make money in a home computer game in 1987, you don't target just one computer. You've got to target a range of them. And what the team faced was something that looked a little bit like this. The most popular and cheapest and most prolific home computer was the Commodore 64 with a whopping 64 kilobytes of RAM and an 8-bit microprocessor. And we'd had the Apple Mac II being released at the other end. The goal was to release a game that could address all of these platforms. And that's going to be a bit of a challenge. They did actually do it. And in 1987, they released the world's first point-and-click adventure game called Maniac Mansion. It's a comedy horror. Basically, a mad scientist kidnaps a girl, and 4 young friends have to go and rescue her. Traditionally, if you're going to create a computer game, you would want to target that small home computer first, the Commodore 64, and you would write your game in assembly. Sounds quite problematic if you're going to try and introduce things like plots and character development and puzzles. This, to give you an idea, is what Hello World looks like in Commodore 64 assembly code. Not the easiest one. So the team went away and said, you know what? We're going to create a runtime and a programming language. And they created the script creation utility for Maniac Mansion. And it solved the problem. It ran on a Sun workstation, and it allowed them to create a game in a graphical style environment with their own programming language and to generate output that cross-compiled to all those target platforms. It sounds like a fantastic solution, but I don't think it was beloved by the developers who used it, because they referred to it as scum. But scum did work. And it addressed all the target platforms that they had to do. And in fact, you can still run Maniac Mansion today in Scum VM, which is an open source project. And all the games that they wrote for it continue to work to this day. Now, if we look at the economics behind this, what the team had to do was decide whether or not it was cheaper to write an application for the Commodore 64 and then port it, essentially rewrite it for every single other platform, or whether or not it was cheaper to create the runtime, write the game for the runtime, and port the runtime to all of the available platforms they had to support. And if we look at the balancer scale, the Scum Balancing Act here, it was indeed cheaper for them to go and write this engine. And it's kind of similar to what we do with WebAssembly today. So I work predominantly in the embedded world. And if we're doing WebAssembly today, here's a bunch of WebAssembly, here's a bunch of real-time operating systems we need to support. And that's just the operating systems. When you take into effect the different chipsets and architectures, there's roughly 6 for each of these, so it's quite a plethora of different platforms that need to be supported. And going back to our balancing act again, you know, it's basically the same thing. It's the same economics, right? It makes sense. Or does it? It should do. But what I want to talk to you today is about where things differ and where there might be problems and what we can do about it. And to start with, let's look at how WebAssembly and its process for approving new features works. You go from a proposal at stage 0 to a ratified standard at stage 5, but perhaps the most interesting stage is 3, where you start to see implementations appearing in the major browsers and tool chains. Now, for us, it kind of looks like this. You get a Firefox and Chrome implementation in Scripton with the probably the chosen compiler architecture for WebAssembly for the web. Eventually, the Inscription team might upsource stuff to Clang, and it gets pulled down into the WASI SDK, and then you get access to it, which is where we are in the embedded space, mainly in the WASI SDK. But there could be multiple proposals all going through this process at the same time. And what does that mean for us? Well, let's imagine I'm going to create an IoT device that looks a bit like Thor's hammer with a couple of aerials stuck on the top. And I've got a ROM image, and I put my WebAssembly runtime on the ROM image. And I know my runtime supports features A, B, and C. Everything's great. I get the latest Clang. I build my C code, and it works. It's fantastic. And that's because my runtime features match my compiler features. But in the standardization process, when you get to stage 3, features are enabled in the tool chain as experimental and default off. When they get to 5, they're often default on. So at some point in the future, when I go to build my next update for my application, I do the same thing. I go to the web, and I pull down the latest Clang, and I go and build it. But now I'm getting features I didn't want turned on, features that my runtime doesn't support. And when I go to run my code on that runtime, it doesn't work. This happened to us with reference types. So let's go back to our scales again. What does this mean? This means I have to do all of this work, plus now I need to maybe maintain a compiler, or at least be aware of what's going on. There's some additional costs I have to take on board because I'm using WebAssembly. Now, often I'm not just building applications using the compiler directly. I'm using WASI, and specifically WASI Preview 1 without the component model at the moment. But I want to use that library. It's very useful. And I would do the same thing. I would just go to the web and pull down the pre-built releases and use those to build my applications. And that should work, right? So I'm managing my compiler. I just pull down the latest releases. I build my stuff, and I link them together, and everything should just work. Except, how does the WASI libraries get built? Well, they get built with the latest Clang. And so it's introducing instructions and opcodes that I don't support in my runtime. And when I link everything together, it just doesn't work. Sometimes the WASI development team turns on additional features that benefit the creation and the maintenance of WASI. And one of those was including debug information. And the result of that was that Hello World jumped from 4.5 kilobytes to nearly 50 for an embedded device. And I've not changed my compiler instruction here. My way I invoke my compiler is exactly the same. So the way I have to solve this is now I have to go and build my own sysroot. So now I'm maintaining a compiler and building a sysroot, and these are the costs I have to carry if I'm going to use WebAssembly. And so I look at my scale, and I add an extra weight. But software, unlike SCUM, the software we're using in WebAssembly, it doesn't exist in isolation. We have other things. We have a huge open source community and a lot of open source software that delivers an awful lot of value. And the Harvard Business School did a report they released in 2024 that said that open source software, to rebuild the open source software that we use most commonly today, would cost $4.15 billion. But that same software delivers to the economy $8.8 trillion of value. And for most development teams, if you had to recreate that additional software that you could use for free, it would increase the development cost by 350%. So having access to open source software is really important. And in the embedded space, we're mainly interested in C-based code, so not the entire set of this, but a huge chunk of stuff is written in C, and we would want to use that. And the most popular operating system for open source software is, of course, Linux, so that's kind of important. But if you go and try and build stuff, and here's a screenshot of what happens out of the box, things don't work. And there's missing features in our API. So our WASI API is kind of narrow. It's not as wide as it could be. And so we don't have access to everything. And we're missing some core WebAssembly features that would make it easy to bring in software. And that makes it difficult too. So if we go back to our scales, we can now add the cost of not having access to all of the software that we need and would like to use. So what can we do about that? Well, I'm involved in the Bytecode Alliance, along with Oscar and many others here. And there's a group called the Embedded Special Interest Group, and I help with that. And what we're attempting to do is create some long-term support. Essentially make sure we get the latest security releases for the important toolchain artifacts and runtimes, and just make sure they're all in sync. The features just work, and they all work out of the box. So other developers, when they come to use this, don't have to pay the cost of maintaining their sysroot and compiler. It's a pretty straightforward proposal. Have a downstream copy, bring in the CVEs and updates, and make sure everything works. And if we did that, we could try and rebalance our scale a little bit and take some of the cost away. We still need to look at how we provide access to the open source software we'd love to use. And that's probably a process of standardization process. You know, with the raw stuff, signal handling would be fantastic. It's a software interrupt. If I had that, I could do a lot of porting of open source software. Past example was set jump and long jump that was missing and gets re-implemented with exception handling. There are other things we would like from the system interface itself, and that's probably a question for the WASI subgroup. So there's some work we could do there too. Let's look right now at how the WASI subgroup works and what goes on with WASI, at least with Preview 1. The WASI group defines a standard set of API specifications, and then every runtime that wants to support WASI has to implement those specifications. And those APIs talk to an underlying operating system. So if you're running on Linux, if you're running on Windows, regardless of the runtime has to implement the same functionality, and it's a duplication of effort and cost. It's the same bit of logic that's going to connect a runtime A to Linux that will connect runtime B to Linux. So is it possible to break these apart? Is it possible to say, look, you just do the runtime, and we'll just deal with the system interface in a different way? And honestly, the inspiration of this comes from a lot of people in the room, Ben and Arjun, and some of the concepts from Carnegie Mellon in the WebAssembly Research Center. And could we break it apart? Could we say, look, runtime A and runtime B, they need to talk to Linux, they need to talk to Windows. Could we provide one binary that both runtimes could use that would provide that system level interface for them? And that would require a universal API for supplying plugins to WebAssembly runtimes. We don't quite have that at the moment. What we do have in terms of a kind of standard is the WebAssembly or the WASM-C API, which defines a common API for embedding runtimes into a host system. But what we really need is a plugin C API that would sit and allow us to bring in multiple system plugins. If we could do this, it would help us, obviously, and I think it would probably help our friends who are developing the component model too. So what would that extended system level interface look like? Well, for academic sake, and because the economics indicate it so, there was a talk from Anil yesterday talking POSIX bad, Linux good. Well, most of the software we want to run runs on Linux, so if we had something that looked like Linux, that would be really nice, wouldn't it? And there's a lot of reasons for that, right? It's becoming almost a de facto standard for development. We all have Windows subsystem for Linux. Apple's introducing containers, which is a Linux API. There's a FreeBSD, has its Linux binary API that exists. There are other examples for WebAssembly, like Wally from Carnegie Mellon, and most recently BrowserPod, which allows you to run some back-end for web development in a browser. So it would be really nice if we could do that. But we don't want to throw away WASI Preview 1 support at all. We still need to support applications that have been built to use it. And you could do this by putting a WASI Preview 1 module in here and just using it to supply the front-end interfaces. At the back end, it would talk to whatever system interface plugin we develop. So let's do a little feasibility study. Is this actually possible? So this started as a concept, and we said, look, could we actually ever do it? And we took WALI because not every browser, every WebAssembly runtime implements WALI. When we started, the only one that did it was WAMR, and that was through the work of Arjun, thank you very much, and Ben and the team at CMU. And we said, look, if we make WALI work on another runtime, it would be pretty binary. It would either work or not work. If we did WASI, we might have skipped something, and because everybody supports it, and it wouldn't be such a good test. Let's use WALI. So let's take WALI, and what we want to do is break it out from WAMR as a standalone library, and we want to make sure we can run it against two different runtimes. So we said, well, we'll relink it to a new version of WAMR that doesn't have WALI support, make sure that works, and then we'll use it with WASM Edge. Just see if we can provide it as a plugin for WASM Edge and see if that would work. And so the binary, we take it out, it's about 120 kilobytes, unoptimized, it's not huge. And it worked. So with WAMR, we can invoke and run WALI-based, there's too many W's here, we can invoke and run WALI-based WebAssembly modules with WAMR, where WAMR doesn't have the WALI built in. So we can supply it as a native library here. You can see it from the command line. And the next bit was, well, that exact same native library, which supports a WAMR interface, could we then take it and get it to run with WASM Edge? And WASM Edge does not support WAMR native interfaces. Could we do that? And the answer is yes. So you can take the exact same binary. So could we reduce the costs of developing system interfaces by just supplying a common interface binary for the platforms that we want to support and allow any runtime that wants to use it to use it? And I think the evidence is there that this might be a feasible option. Now, it's not a perfect solution. This is just proof of concept and just an academic exercise just to show that we could do it, but it plants the seeds where we could go. So let's go back to our scales again. Now, if we did this and we could provide support for Linux-like software, then we can really, really start to rebalance our scales and get back to where we were. Now, this might seem that I'm not particularly fond of some of the standard stuff, and I've been quite critical, and that's not true. Standards are really important, and the formal specifications of the standards are really, really great. They offer something that I think no other runtime really has at all. One of the problems we've been looking at in the embedded space is often our solutions want to be embedded into safety critical or certified environments. And they are very expensive environments to update and maintain software for. And there's this problem called mixed criticality, where you've got a safety critical system, but you want to run some non-safety critical code on it. An example might be an airline wanting to get metrics off a black box in the aircraft to see whether or not their pilots are doing the right thing. Could you do that? Well, not today, not without extra hardware. Just because it's so cost ineffective to update certified software and get it recertified, that what most people do is they just pay the cost of extra hardware, have two completely separate systems, and have a hardware link between the two. This works, but it's expensive. If you could do it all in software, it would be cheaper. What if you could have a certified sandbox? And inside that certified sandbox, we can run our non-safe application, whatever it might be. Or metrics collection from a black box, metrics collection from a piece of machinery in an FDA-approved manufacturing process for healthcare equipment. That would be really important. Is it possible to do? Well, yeah, we've got SpecTec, right? We've got this formally specified runtime. We can verify, well, it's formally specified language. If we could do that, and if we could have a verified runtime and a certification authority that would take that and say, yes, we certify you could use that in a safety critical environment, or at least in our critical environment, whatever it happens to be. If we could do that, then we could have a cost-effective way of inserting non-safety critical code into that environment and solve this cost point problem. And that, in those environments, would really tip the scale. Now, I mentioned Tunahead earlier. So where did that come from? the opening scenes of Maniac Mansion. The characters are debating whether or not they're brave enough to go into the Maniac's house. And one of the lead characters says, well, if anybody wants to back out, you can do so now. And in the original plot, and the original script, the authors, a guy called Ron Gilbert, he really wanted his character one of his characters to walk out. The nerdy guy would walk out in fear. And the main character would call after him and say, don't be a, and I don't think I could say this at a conference, but it is a something head. You can take the first few letters of these words and work it out. And George Lucas is like, you can't put that in a computer game. You can't. We're going to sell this to kids on a Commodore 64 playing at home. They can't have swear words in them. So instead, it became, Bernard, don't be a Tunahead. So that's my talk. Thank you very much.
Thanks so much, Chris. So plenty of time for questions. How do you feel about concurrency and shared everything threads?
So not in the talk, but a lot of what we're doing at Siemens is concurrent WebAssembly. So yes for concurrency and yes for shared everything threads, please.
Do you have a runtime that you would like someone to stamp, or do you think it would sort of need to be written fresh with certification in mind?
I imagine it would need to be written fresh with certification in mind. But I wonder if part of that could be mechanized. I don't know.
I guess you should talk with Sandrine, but I think she's attending another session. So.
Hi, thanks for the talk. I also have a question about certification.
Yes.
I was wondering what you had in mind there, because in industry, my understanding is there's a notion, well, and government, there's a notion of what certification means for software, and it is not probably what a lot of the people at this event would think of. Not formal verification, but sort of building lots of processes and testing frameworks and so forth.
Right.
What did you have in mind? Was that both formal verification and ISO, whatever it is?
Yeah, it would probably be, realistically, it's probably going to be a combination of the two. But what we've seen in this world is the German Aerospace Authority, DLR, working on a safe WebAssembly runtime. Not particularly fast, but safe. That would be really interesting. But there's different levels of safety certification. So there's safety certification for cars and for rail and for aerospace, and probably aerospace is one of the most challenging. And there's different levels of it. And what we're attempting to do is find out, can we talk to these certification authorities and find out exactly what they would need and what could we do with it? And I'm heartened by the work to get C++ compilers with formal verification working for Airbus. So maybe there's something we could do there.
Right, I mean, I'm thinking maybe something more tractable than what we might have in mind might be a good starting point. Yeah.
Indeed.
Chris, thanks for a lovely talk. I liked your idea of a plugin for these kind of system-specific interfaces. Would that be useful for other language runtimes apart from WebAssembly, or should everyone just be targeting WebAssembly anyway?
Well, I'd like to think everything targets WebAssembly, but I do think it would be interesting for other language runtimes as well. The question I would have, we started to explore exactly what we need to implement in that API interface to make it work and support. I say we, I mean me and folks at the WebAssembly Research Center trying to work together on it and trying to make some effort here and move this along. But it would be an interesting question. What do we need to provide in that interface to allow threads to work, interaction with the operating system? Stuff that's not already in WebAssembly CA. So that would be a good one. Indeed, for the functionality by the runtime to
runtimes don't need to implement anything except provide support for this interface.
Thank you.